Hi everyone, welcome back to Stats. So you'll remember that before the quiz, we were talking about t-tests. So t-tests are for the specific case where you're comparing two specific groups. So there's a lot of cases where you're going to want to do that. You have an experimental group and a control group is one of those instances, or really any circumstance where comparing two groups is fine. But you might want to compare more than two groups. So we're going to talk with Raja, and I'm bringing him back for this video, talk a little bit about a different type of analysis that we use when there's either three groups we're comparing or more than three groups we're comparing. So I was actually going to have Raja come along for the quiz 2 review from the last video, but it was storming outside when I was reviewing that, and he was hiding under the pillows. So I figured that probably wasn't a good idea, but storm's over, Raj is feeling a little bit better, so now he's ready to learn about something that is referred to as an analysis of variance, despite how tired he looks. He's obviously very excited by that. So like I mentioned in the last video, I'm feeling a little bit under the weather, so if my voice is a little bit hard to hear, not super hyped up about things, that's why. But we'll just try to get through this. So there's, again, going to be many instances where you want to compare more than two groups. You don't want to just, collapse those down into two comparison groups. That wouldn't make any sense. So let's say that you're in a situation where you want to compare an experimental group for drug 1 and drug 2 to a control group. So that might be a case where you don't want to just collapse them against both drugs. You want to see if one drug is better than a control group or better than a placebo, or you could have a control group plus a placebo condition plus another drug condition, and then you can see, are there differences overall? You can compare across multiple groups. You might also have a ton of groups that you're looking at. So if you're looking at GPA at Connecticut universities, you would want to look at all Connecticut universities, and you want to get a mean and standard deviation for all of them and see if GPA matters in terms of differences across Connecticut universities, and if there is a difference, how big that difference is. Again, you might want to look at this in developmental psychology. So you might look at ages across different age ranges. And so you might be looking at social skills, and you have kids ranging in age from 3 to 7. You might break that apart so that you're looking at what is the average level of social skills for 3, 4, 5, 6, and 7-year-old. And then you don't have to split it between just younger kids and older kids, because there might be differences between a 4 and 5-year-old, but not between a 3 and 4-year-old, or between a 5 and 7-year-old if there's, say, critical ages going on. So that might be valuable to you. So with this, we use something that you often see shortened to ANOVA, and it's pronounced ANOVA. So that is just an analysis of variance. And so when we go through this in R, there's going to be a lot of steps. So I'm going to walk through the more basic version of it, where you're looking at differences in means, and there's a bunch of different means. So analysis of variance is called that because there's an overall variance in the outcome variable or the dependent variable that you're interested in. So a clinical trial for depression rates might be the level of depression for participants. So you have all of that variance, and then you're looking to see how much of that is differences between those means and how much of that is differences within each of those groups. So first of all, because we're doing null hypothesis significance testing, you're starting out with a null hypothesis that all of those means are equal to each other. So if it's 3 means, it's that the 3 means are equal to each other, that any differences that you might see are no more than random chance. The alternative hypothesis then is that there are some differences between the means. And so when you're looking at this, I have an example A and example B here. So first of all, let's take a look at example A. So what you're seeing is that there's variance that's between groups. So that's differences between the means. And there's within group variance. You also see that here there's also between group and within group variance. So if you're looking at A and B, what you see here is that for A, and Raja is getting bored. So for group A, you see that there's not that huge of a difference in the means. But within each of those groups, there's a lot of variability. So it's not as big of a difference. What you see over here is that there's bigger differences between groups. So those means seem to be further apart from each other. And so within groups, there's also less variability here. So within each of those groups, there seems to be more in common. So what we would see here is that here there seems to be more variability within groups than between groups. So that difference between the means isn't as impressive. Here, the groups seem to be very different from each other. A lot of the variability is between groups, but within groups, there isn't as much variability. So when we're doing an analysis of variance or an ANOVA, basically we're going to be doing some mathematical calculations based on this, where we look at the proportion of variance. So if there's more between groups variance, that's a bigger difference and you get a bigger F score. If more of the variability is actually within the groups rather than between the groups, you get a smaller F score. And so what you'll get here is you'll get an F statistic. And you interpret the F statistic similarly to how you would interpret a T statistic. And so rather than there being a distribution that's close to normal, the F distribution actually starts at 0 and goes up to infinity. And so what you'll find is that most of the distribution is going to be at the bottom of that distribution. Lower F scores are more common than higher F scores. And then we're going to be doing a test, which is a one-tailed test in this instance. So for it to be within a certain extreme of a value, for an F test, it has to be above a certain value. So anything below that critical value for an F will not be statistically significant. Anything above that will be statistically significant. And it works, again, the same way as for chi-squared and t-test, where we choose this based on our alpha level. And you'll see, for example, down here, that if the alpha is 0.05, it's the 5% most extreme F values that we would find by random chance if the null hypothesis that all of the means are equal is true. So a different distribution, a different set of means, but as we'll see, a lot of the interpretation builds off of what we would do if we just had two means and we were doing a t-test. So with that, let's bring Raja along and we'll do some analyses in R. See you there.